Okay, much better. Now I see my slides. Okay. Hello, everybody. Thank you for the introduction. So my name is Riccardo, and I'm a PhD student in Politecnico di Milano. I'm a little nervous because here you do all this core-based stuff, and I actually work on top of all these things. So thank you first. And I'll try to give you an idea of what I do and why I use containers, in particularly Docker. You might have seen one of these pictures in the last 10 years, I guess, which are describing that the web, in general, the internet, but the web is moving very fast, and in 60 seconds, a lot of things are generated. Some people, like my group, are doing research on these things, and we are trying to making sense of them. But since they are produced very fast and they are very heterogeneous, some challenges come up, and you need to remove noise. You need to integrate this data in order to, do some analytics on top of them. The thing is that in order to solve this problem, you need to put together a lot of different areas. In particular, you need to do stream processing because they're fast. You have to do data integration, and the rule of thumb, all the theory there comes from the semantic web area. I don't know if you heard about semantic web. I think you will after the talk. So then you have logic, database theory, machine learning, and big data in general. We're doing quite well in the sense that in 10 years of the community produces about 1,000 papers. So we're growing fast as the data we are trying to process. So I'm happy about that. And the jargon that you can refer to is stream reasoning. That's the name of this research field that drives data analytics through the semantic technologies, which practically means exploiting the metadata. And here you can start matching why containers are relevant for us. And so the thing is that we want to be responsive. And we process data on the fly. As you can imagine, a system that does all these things together, it is quite complex, like this complex, right? Like a giant shuttle engine that can answer your query in continuous. And since it is a research field, everybody does his own approach. So you got like this, the one I show you, then you have the long one, which different semantics of execution, and putting them together is a mess, especially when you realize that they can be distributed. And recently, if you are in the big data world a little bit, you might have heard about, for sure, Spark streaming, Flink, but also Heron and whatever. When you try to use this system to do data integration and stream processing together, you might face more challenges. So how to evaluate this system, how to benchmark them is an open problem. Like there is no solution. And the thing is that there is no agreement of what to measure. Like the guy there is measuring the depth of the river, the other the width, but nobody agrees on what is relevant and what is not. So research-wise, is tricky to see what performs better than the other. And probably most of us are still using the wrong tools to measure what we want to measure, right? So I asked the Tuk, and I asked him, what should I do to measure my tools, my applications, my system? And he replied me, use containers, because containers hide something behind a level of complexity which is reasonable. You can scale them up and down, so you can observe. Observability, what we were looking for, right? You can monitor containers, even in a distributed environment, and you can use all the nice tools that we saw today, and we will also see tomorrow. You can isolate each part, and you can observe both microscopic and microscopic behaviors, which is pretty cool for us, and allow us to correlate performance metrics to the architectural choice for solving the problem we want to solve. Two more cool things that containers do for us is actually providing repeatability and reproducibility. So as researchers, we care about these things. We want our results to be as general as possible. And actually, all the nice things like in Docker files documents how you build image, and you produce a lot of things out of your building process that can be used to correlate, to trace it and capture the provenance of it. And that's how the registries and distribution system provisioning system work in practice. Moreover, as I was saying, you can test your experiment in different environments, right? This open up a new idea to do computational experiments, a new way to do it, which basically means building a vector of your experimental features, your experimental parameter, and computing it in a combinatorial way, so you can correlate it automatically, like you do your library for your analytics, and you do that. If you think about Docker and other container systems are full of this metadata already. We don't have to invent anything new. They already carry all the information we want. So the question was, what if we could run these analyses directly in either the registry or the container manager, which is pretty much what people that try to check vulnerability of software do, right? They cross-check the image metadata with the knowledge bases about software vulnerabilities, and they come up with new analysis. What if it's the registry that does that for you automatically, right? So now I'll do a step back, and I will deep down in another section, like in the role of metadata, in particular of linked data, which is where this idea came from originally, like the way of data integration using common shared knowledge. How many of you have heard about linked data? Ever? One? Just one? Two? Okay. So how many of you knew Tim Berners-Lee? Okay, that's more famous. Okay, I'm happy about that. So Tim Berners-Lee, besides inventing the www, I mean, one of those, also said this sentence, that the web should be exposed and shared in a way which is processable both from machine and human independently. And the cool thing is connecting knowledge through these links that can be traversed by machines, so you can discover new things by the time you are consuming what you are currently consuming, right? And this creates this jargon of knowledge graphs, right? These are very popular right now. Knowledge graphs, like connection of different concepts across web resources. Tim Berners-Lee and his research group provide us a set of principles that tell us how to build this linked data world. The first principle is about URIs, like to uniquely identify things on the web, which sounds simple, but it's a mess. If you ever face the problem of naming, besides in computer science, which is a problem itself, like naming on the web with DNS, it's a problem, right? So, but if you guarantee this unicity in naming, you can identify things. But moreover, everything should provision it through HTTP, and content negotiation is the way the server communicates with the client in order to provision the best representation possible of the information he requires. So if you check a URI with your browser, basically you will get a web page. If you check your URI, you fetch your URI through your script, you might receive a JSON that represents the same content in a way which is machine processable. Okay? As I already mentioned, interlinking, it's the crucial point, right? My current source should link new other sources that are also uniquely identified, creating this huge network. And this should be done using semantic web standards, which I will show you in 1 minute. So to show you how much this become popular in the recent 15 years, this is the current LOD cloud, okay, which is a huge knowledge graph, only the open data, not all the private ones, which are also there, right? But we don't link them, of course. And we are talking about like several thousands of gigabytes of data per country. So like governments also participate in this, publishing their own data to make them transparent to the citizen. But something is missing here, right? I told you the principle, but how can this thing be really connected? And the last point of the principle, the semantic web standard, was actually the interface to all a set of technologies that we need to use. The first one is Vocabularies. You might have heard about schema.org. I think so, right? Because you work with, you know, web technologies at least. So Vocabulary collect this knowledge about specific domains and allow you to reuse it in other domains. And is a first step towards this interlinking that we were looking for, right? So I define what is a person, and Facebook, Twitter, whatever social network you're using, refer to this concept with their own representation. So we know that when I fetch a user in Facebook, I'm speaking about a person or a page, whatever concept you are describing, right? But this should be unambiguous. In this way, machine can get it completely. So we can annotate this data, and the disambiguation gives us the possibility to do queries, like in databases. Databases are easy because they were disclosed in comparison to the web, where everybody can do whatever he wants, right? So we need to ensure this disambiguation, adding one level of abstraction that everybody refers to. The standard data model to build this data is called RDF, Resource Description Framework, which is basically the simplest element to build a graph, a triple. Subject, predicate, object. Subject is your own instance of person, like so Riccardo, for instance. I will show you an example. The predicate is a verb, something that entails an action or something you want to do. And the object is the resource you're targeting, for instance, a person. Triples connect each other due to the unique name assumption, the URI we are describing, and create the graph you want to have automatically. For instance, Riccardo, me, I'm an instance. Let's say I have a URI, like my web page, for instance. Presents at is a property that is available in schema.org, so I can use it. And the Linux Lab is another instance, like the web page of this conference, okay? And I can say Riccardo is a person. Person exists in schema.org also, so it's an entity everybody recognizes. Sorry, this is I knew that. Sorry, all the conference. I will check. I will change it afterwards. I'm sorry. Like Linux Lab is also a conference, and it is located in Florence. Okay, so we have all this property that creates my graph, right? If I want to show it as a graph, I can easily navigate it through different entities and move up and down and following the links to answer my query. So if I'm looking for all the people that presents at Linux Lab, it's easy for me because I just have to follow the path, okay, and I will fetch my answer regardless where the answer is actually stored, right? So let's assume you have this web service that exposed me to this data, which are called repositories, by the way. How this can be useful for containers. So the thing is, how do we link containers together? Can we lift container to the level of this open graph that I showed you before? Let's discuss it. Like think about containers and metadata. Docker files, but in general manifests, the YAML file of Kubernetes are metadata. Images are annotated with regard to the build process, right? So I can trace it, and I will show you an example. Containers orchestration relies on these annotation metrics. Like Kubernetes, in order to know which container has to switch on and off, how to migrate it, needs to read this metadata. So we have them already. So let's try to now define some principle for linked containers, like following the example of principle for linked data. Okay? So we have images container are uniquely identified and interlinked. That's obvious. Like when I spawn a container, it would be a uniquely identified instance. So I don't have to guarantee this. It's by design guaranteed. And it links because in a microservice architecture, it communicates with others through the method it exposes. So I already have all the ingredients to create my graph of containers. Images are provisioned and containers are orchestrated through web technologies, right? Like Docker Hub can be fetched to different endpoints, And they also already do content negotiation, because if I ask a research from the web interface, I will get something. If I ask it from my Docker daemon, I will get something else. So I'm already there. So last but not least, we are working towards standard already. The Open Container Initiative is working towards that for runtime and the metadata required for it. But also the Cloud Native Foundation is doing some effort in that direction. So if I envision this open cloud, linked open data with Docker and the Kubernetes and OpenShift and whatever you want to use for your container solution, I mean, we can see them there, right? So what is missing now? Let's ask again the penguin. Again, vocabularies. We need to interpret this manifest data, but also the image and the container. So a little disclaimer before I show you the example. It might look a little verbose, because now I'm porting what is a Docker file into RDF. So you see Docker file is a Docker file, and guess what? And it contains some instructions. And each instruction, like extraction 1, executes a do, Docker from, like I'm starting from an image, and I'm getting the value Ubuntu latest, and I'm fetching that with a comment. I'm attaching a comment to it, and I'm exposing myself as a creator. And I'm also listing the other execution, like I do apt-get to update my image, and so on and so forth. Two points here. I don't want you to do the way you do, to change the way you do things. Like you will keep describing your Docker file as they do. This translation is automatic. I just have to define the vocabulary, which is actually the Docker documentation. So it's already defined. And now this is queryable, because I can put it into a repository, just do the automatic translation, and I can run query using the query language called SPARQL that I showed you before an example. One more thing is that if this is written in JSON, I don't even have to do the translation, because JSON-LD matches one-to-one data and linked data. Just attaching the context I want to use for the interpretation, I can do that with no cost of annotation, for free. I also have to describe the workflows, though, like the building process and the deploy and the orchestrations. Like all these things should be captured. No problem. I can do that. Like my build trace of image 1 is related to the execution of my Docker file 1 through my daemon. Daemon 1 is the daemon of my laptop, let's say, or the daemon of the server I'm using for the building, or the Travis I'm using for continuous integration. And I can save all the intermediate stages, and I can interlink them together, so I will be able to fetch them across the web. And this is also queryable, both from a human perspective and from a machine perspective. Because the query I showed you before, I will give another example, are expressible also using the same data model. Sorry, okay, oops. I messed up with never put animation in your slides. They will work against you. So we can guarantee the observability of the internal processes at runtime, because we can execute this query manually through a query language which is not more scary than SQL, and is a graph query language which allows us to do like a nice thing like path. Give me all the images away from these of 2 or 3 hops. So now we can get Queryable Registry in the end, because they rely on this technology already, and they can exploit semantic metadata because we provide them how to do them, and they can negotiate the content with us as they do in linked data standards. But we can do more than this. We can do context-aware orchestration, because we have a clear metadata semantics. And doesn't matter if you're running Kubernetes or another container orchestration system, because as long as we have a common vocabulary that everybody refers to, my query doesn't change. is responsible of the vocabulary to let the system know how to translate it. This can be done in real time by using the technologies I was mentioning in the beginning, like those that integrate them on the fly, like stream reasoning, my research, so use it. And it can be used for monitoring as well, right? So I can combine this integration with the performance metrics also, and have them both together in the same context. And I can drive my orchestration using all this information that before were a privilege of the system that was actually doing the actuation. How does it look? A query like this, pretty much like this, like give me all the Docker files that corresponds that have a creator C, that contains an instruction, and the starting point is Ubuntu latest. This supports also like multi-layered images, whatever you want. Is a graph, doesn't have a hierarchy on purpose. But what else I can do? Like, what are the work in progress of this application? So we already started with the vocabulary for Docker files, which was designed to work with the University of Ghent in Belgium. So if you like beer, you can also go there. And was published in the latest Semantic Web Conference, International Semantic Web Conference in Vienna. And now we are working with a W3C working group to extend this ontology to introduce containers, images, Docker composes. And we are keeping an eye on the work of the OCI to see what they are doing and let them define the standards and just port them in a way which are semantically aware. We can do image discovery by identifying the images through constraint language. So the query language I show you can actually be enriched with constraint languages like SPARQL or Spin. You can check them online. Allowing me to create this, enabling discoverability. I can do that on-demand building because I can output a graph out of my graph query. So I create a new image out of a set of images that match my query. And I can do a federation, like distributing them across the web, because now I can uniquely identify them. And I can lift this federation at the application level. OK, this is pretty much what I already said. One more thing is security is that cross-checking them with metadata about the vulnerabilities is easier, because when I have this representation of everything as a graph, as I told you, triple merges automatically, exploiting the URIs, and just having a similar interface to the vulnerabilities knowledge bases, it's easy for me to combine them. Smart policies are also possible because I can interpret these metadata with a clear semantics, and I can also identify potential anomalies by using starter logic techniques that exploit these semantics to say, if you're combining A with B, most likely your output will be C, which is vulnerable. That can be done before building, which is pretty cool because you don't have to build. So that's everything on my side. I hope I didn't kill you and I didn't bore you with all this web and weird stuff. Thank you for listening.
Question. Do you have any questions? Yeah.
Hello, thank you. The question is, the work you're doing, your group is doing in defining this kind of ontology, if I understand correctly, of Docker only?
No, we started with Docker because it's the simplest, and we also do in the systems, not only the ontologies. Like the ontology for us is the first step.
Yeah, so
because it's the science behind the systems.
Okay.
Yeah, but we are a computer engineering group, so we care about prototyping. So what was the question anyway?
Right, the question was, so if you are including also other kind of container environment, or you quoted the open container initiative.
Yeah.
So you are waiting that the standards, as you said.
Yeah, we're not waiting in the sense that we are checking what they are currently doing,
Of
and
course.
we concurrently do.
Yes.
But definitely we don't aim at defining ourselves the standards, because our technology has to serve one purpose, and the purpose is what the OCI says, in my opinion. They are caring about making the minimal level of standards they need, and it's a good thing for us, because we want to build on top of this to add a new service. So yeah, we definitely want to go more than Docker. Docker was a starting point, which is user-friendly, also in terms of metadata.
Okay. So you're actually using this right now, and because my fear when I hear about RDF or semantic or linked data is, okay, cool, this is now a research project, and we will see results in 10, 15 years. Like it was.
No, the timing is much.
It's much short.
Actually, so I didn't say something in the talk because it was a little too technical on my side. We don't want to annotate anything. There is something called virtual RDF. So basically what we do is we translate the query. We define the vocabularies, we define the queries you want to have, and then we translate them in something the system can actually answer already, which is pretty simplifies a lot in shorten a lot timing of developing, right? Because you don't have to change the architecture you are talking to, which is. But yeah, so we plan to do an application. I currently have a student who is doing his thesis on this, and he's working on Kubernetes.
Thank you. Any other question? Okay, so thank you, Riccardo.